I will go review some important notes for shape memory materials. I think some of the contents you have already got it at the early class, but I will review it like in whole picture, so you can see the big picture of the shape memory materials. So if you see the shape memory materials, so from the materials you have so-called the stimuli, right? It can change the materials in either physical property or chemical property, but most the shape memory materials we discussed, like in the early class, it's for the physical property, so it will change the shape. So there are two notes here that differentiate the shape memory material and shape change material. So if the reactions is instantaneous, really fast, you can call it this shape change material. But if it has like a program to memorize the shape, so it will have the memory, we call it the shape memory materials. So this is some examples: alloy, polymer, hybrid, its combinations, ceramic, gel, and also the composite, all the combination of this. Okay. So we start with the shape memory alloys. In general, there are two categories: thermal and magnetic. So the stimuli using the heat, and the second using the magnetic. To remember these two responsive alloy, both are reversible Martin-Synthetic transformation, meaning they can, if it is heat, you can heat it and then cool it, and it will cycle around that form. And for alloy, I think there are three major types: copper, nitinol, and barium, the iron. And the phenomenon, I think you already get used to know this phenomenon, okay, because it's already well established. So you should already well known of this process. So there are at least six processes. So from here, for number one, so from austenite, it gets to here, the martensite, the twin martensite. So it has a twinning, but it has a double twinning here. And then when you are unloading, it will bring back the austenite form. And then if you load the twin martensite, it will get to the twin martensite. If you're heating or cooling, you will get the twin martensite or austenite. So the right part here is this. It is actually usually it's for the loading. So if you are loading with some applied force, you will change the form from austenite to the twin martensite. Or if you are change the temperature, will change the austenite and twin martensite. Yeah, there are some notes here, and this is the I think this is the nitinol, the examples, how they remembering the shape. And then the shape memory effect and superelasticity, it's different in this stress strain graph. So superelasticity is this shape changing material, like I mentioned before. So it will react really fast. instantaneously. Like here, you will see when it's loading, it's going pretty fast here. And when it goes unloading, it will back to the original point. Okay. And for shape memory effect, you have some loading here, and when the unloading, it's actually goes here, the string. But if you are stimuli the material with the heat, then it will revert back to the original shape. So that's why you have the twin martensite and twin martensite. The difference is the loading and unloading, and heating and cooling. So that's so the shape memory effect, it will take time for the material to revert back to original shape because it needs another stimuli, another trigger effect from the heat. Okay. So the other material is the polymers, and I think this is the most applicable because there are a lot of polymer types that can be used as shape memory polymers. And this is the advantage compared with the alloy. The density, fabrication. So fabrication means when you are trying to make in a large scale product in industry, if you have lower energy to process the material, then you will easily fabricate a lot of product, right? And then the third one is the recoverable strain is normally a higher order than the alloy, meaning if you are stretch your polymer really like in a long shape, then if you try to compare with the alloy, the metals, when you try to recover that displacement, revert back to the original shape, the order in polymer is really high compared with the alloy. And then easy to tailor the thermomechanical property. And then you can also make it transparent for polymers, easy to be transparent. Yeah, I think there are several, I'm not sure it's still there yet, but a few years ago, there are some research for making metals transparent, but I'm still not sure that. And then shape recovery temperature range, it can be altered easily. So meaning the temperature to change the shape, you can alter the range. And then also the polymers, you can recycle, reuse, excellent stability for chemical. Most of them biocompatible, and some of them biodegradable. So biocompatible meaning it's compatible or you can use it in biological environment. Biodegradable means if you are put in the biological environment, it will degrade. Right? So yeah, and then you can use it as drug carrier because it's biocompatible. You can use it as a drug carrier, and then you can have a lot of stimuli. There are some polymers you can use heat, increasing the temperature, or moisture, like mostly hydrogel, acidity, the pH, change the pH, change the shape also, and then light. So you can have light as your stimuli. So you can switch the molecular shape inside the polymer. And then you can design for more than one stimuli. You can easily design that. And then you can have multiple shape memory effect by synthesis or programming. Meaning programming, you program the memory. Okay. And the difference for the polymer and alloy is in the mechanism. So this is the basic mechanism for polymer. I think I've talked this before, but not in really detail. So this is the details So in the shape memory polymers, usually you have two segments in polymer. This black one here, like a spring here, is the elastic segment. Okay? And the gray one here is the transition segment. Okay? So you have two segments. And then if you are changing the temperature in the higher temperature, the transition segments, like the gray one inside, it becomes soft and easy to be deformed. But the elastic segment, it stays as it is. So when you are deforming the polymers, you're actually deforming the transition segments. While the elastic segment, it will go along the way with the transition segment. And then when you are decrease the temperature, the soft segment will become hard, okay? And it will stay at this fixed length. Okay? And then when you heat this, the gray one will soften. Okay? When the gray one softens, it will goes back to the original shape. So why it goes back to the original shape? Because the black one is, remember, it's elastic segment. So it will be when there is no applied force from the transition segment, when you plastically deform, it will revert back to the original shape. Okay. And then the left graph is the difference, the shape memory polymers. So if you see here, this is shape memory polymers. This is shape memory alloy. So you will see the temperature stiffness graph. So while this polymer, in the low temperature, it has a high stiffness. And when you increase the temperature, as you see in the picture before, the elastic and transition segment, the stiffness will goes down as the temperature increasing because of the transition segments become softened. But for the alloy, it starts from here, the stiffness, you start from the temperature. So temperature increase, and that way the stiffness is harder, because when you are increasing the temperature, you cooling the temperature, there are martensitic transformation. So that's why. So some shape memory polymers, normally they are hard at low temperatures and soft at high temperatures. It's opposite from the shape memory alloy. And then in details, okay, if you see this graph here, the red one is the switching segment, okay, meaning the transition. And then the blue one is also the switching segment. It's elongated and fixed here. So red one is for the relaxed. So blue one is the elongated and fixed. So when you have this red one, you go for extension and cooling. It becomes here, and heating bring back to the original shape. And you can have several design actually. So this A, B, C, D. So A is just as normal switching segments linking with the gray dot point here. It's the net point. Okay. And then for B, you can have the switching segment in a side change. The red one here. You can design like this also. And then the C, you can have the switching segment as a functional groups. So the functional groups here they can easily form a covalent bond, reversible covalent bond. And then you can also have a ABA tri-block segment. So you have blue, red, blue at a segment of polymer, and then linking with this gray dot here. You can have this mechanism all of this. So you can design the polymers by molecule. So you can either synthesize, mostly synthesize, or maybe using the melting process and then blend all together. You can also do that, but mostly the easiest one is and the most versatile use is by synthesize. So you have the monomer, and you want to link all the monomer, whatever you want, really. Okay. The limitation is you need to know the reactions, how to decide the reactions, and then you can design all of this. Okay. That's the shape memory polymers. And then I will only discuss the alloy polymer and then the hybrid. The ceramic and gel, I think, already covered in the early classes. So the shape memory hybrid, uh, it's the how to combine the advantage of the polymers because it's easy to be tailored, but the synthesis of the polymer itself, we need to have a good experience, at least for the polymer background. So hybrid can actually be a solution. So we can involving any, for example, here you can have the matrix is metal, organic, inorganic, and the inclusion is also that type of materials. You can combine these materials and make your own hybrid material. So you can have the matrix and inclusion not only for polymers, but also you can select from any materials. So some features here, you can see there are, this is thermo-responsive shape memory hybrid, this original shape. This is the multi stimuli responsive shape memory hybrid, and then this is quite interesting. This is the pressure responsive shape memory hybrid. So you can utilize pressure to stimulate the effect, and then you have rubber-like shape memory hybrid with repeated instance of healing functions here. So you can have the alloy as the spring, and the hybrid is here. So when you cut open this material, and then the spring, it will trigger some effect so that these two can be together, and then linking with the hybrid itself. So you can, I think it's applying some electric, so it can be linked together. So that is shape memory hybrid. And then some typical applications, I think for alloy, mostly this is the usage. Okay? You can have the shape memory alloy for your MEMS or micro electromechanical systems, electrical device, actuators, or grippers in aerospace, space applications, micro vehicles, energy conversion. It's already well established, especially in this area. And then for the polymers, mostly it's using for medical applications. And surface patterning, making the pattern for this surface. For assembly, disassembly, and then for morphing wings and deployable structures. So this is some equipment that have been established. You have this is the A is the reflector, antenna reflector. B is it's actually a fabric, it's a dress, but the fiber is from the shape closing, and F is the morphing wings. So you can have the wings for aeroplane that can change its shape. It can morph its shape depending on the fluid, depending on the turbulence. And then G, spoons for handicapped people, so it will fix in their hands. And then H, that is the intravenous cannula for the shape memory polymer. So how to develop this material? First is the design. So you know from the concept design, you need to decide or determine the important temperature, for example, or any property that can change the shape. For this example, it is the temperature. So how does it start and how does it end? And you know the mechanism behind. Okay. So if you utilize the Martin-Synthetic transformation and you know the necessary property and necessary behavior, then the next stage is try to make some prototype, okay, and then try to make a large scale, and then see the environment analysis. So this is actually the design for Bloom Pavilion. So it's this kind of architecture. So it will change its shape because of the thermal differences. Okay. So because of we need to know how long this Bloom Pavilion can hold, or how is the cycle. We need to test the environment. That's why we need to have a long-term performance test of a hygromorphic skin system. So this is just an example for how to develop the smart materials. And I have some additional information. Actually, there are some additional information, but I choose this liquid crystal polymers because I think this is quite interesting, because the polymers, mostly they are, if they are like an elastomer or rubber, they have an amorph structure. But in a crystalline polymers, you will have you have directions. Okay? You have a crystal structure. So in shape changing and mechanical property, they have an isotropic property. So it depends on the crystal directions. So some of the crystal polymers, they have rapid and large reversible shape memory materials. So it can be fully reversible, and it has a large amplitude. It can be stimulated by temperature or light. So if you see here, A is the phase transition from left to right here. So it will shape change the polymer chain, suffering from the anisotropic deformation to its coiled conformation above the mnemonic to isotropic phase transition. The terms is not really important for now, but at least you know that you can have a phase transition between this. And then B is when you are using the photo-induced to bend the azobenzene. So if you heard any azo in chemicals, it has the structure. Azobenzene contain the crystal polymers, but transits photochemical phases in the surface. Yeah, it's chemistry. So this UV light, and then the azobenzene before it's trans, and then it becomes cis here. So it's trans, and then it's become like the R going up. Okay. any materials. So by doing this, you can have a bend structure, like bending structure. So you take the line, it will bend. So you have, for this polymer, you have thermal and photo mechanism. For thermal, so A, B, C, you have three picture here. So picture A is three array with plus one radial defects that can be actuated to generate periodical topographical structures. The polymer was fold, fixed, and light in this program with this wavelength, resulting in unfolding at high temperature and folding during cooling, and then programmable shape morphing by 3D printing process. So if you see here, so this is the chemical, the R is this material. So this is 3 by 3 array in 175 degree. So before it is just a flat shape, and then it can make this shape. So this is the interesting point for crystal polymers, because in some point the structure can be crystalline. So you can actually design the crystal structures for the polymers. And here you have this structure, and the interesting point is when you are cooling the structure, it can be folded and unfolded, depends on the temperature. So again, the effect for the crystal in polymer, you can have or you can design in any way you want, if you know the molecules and if you know the reactions. And here you can make all this kind of structure from the 3D printing process. The chemical structure reactions, etc., is not really important to memorize, but at least you know the basic element of all this process is the crystal structures. Okay. So you can design like having a crystal structure like this, or like a cubical, triangle, circular. Depends on how you design. Depends on the molecular design inside the materials. And then you have the light. So A, B, C. So three pictures here. So first is the picture of some monomers, and then the photograph as prepared assembly film bending towards the laser. Okay, so you have laser with the wavelength is 600 wavelength. When you are infuse the material, it will have this shape, bending shape. Okay, and then the B is actually the structure of the artery walls of tubular microactuator. So it's similar to our artery vascular in the vascular system. And then manipulation of fluid propulsion by photoinduced tubular microactuator. So you will see it will change the placement, depends on the laser here. So it will change the positions. The C is the chemical structure of the this polymer here, and this is the picture how the material, it can have the oscillatory motions. So it can have see this it's from 0, 0 0.2, 0 0.4, 0.6. It will move like an oscillations really fast. So it moves because of the sun exposure. So you can have oscillation here because of the sunlight. And this is this one. For the artery posterior wall. So this is the elastic layer, this is the muscle layer, and this is the mesogen. So you have the backbone, you have some spacer here, and then photoresponsive mesogen. So the spacer, so this photoresponsive mesogen will move depend on the light. Okay. So I think that's all the some additional information for the shape memory material. I'm planning to having a quiz, but I think it will be in uh, maybe next 2 weeks. So next week, it's in Tuesday. Yeah, in Tuesday I will post in Moodle in details what the topics. Um, and I think the question is not like the your first quiz is mostly general knowledge of the course, right? So the questions maybe about the advanced technology, like from the middle of our course until now. Not necessary uh, to write down as similar as the content of the courses. So it's not necessary like that. As long as you get the point and you understand the knowledge behind it, and also there will be some questions about the how to develop the next smart materials. Yeah, just like an essay, semi essay. So yeah, I will further notice on the Moodle system. So be prepared for the next 2 weeks for quiz. I think it will be on the Tuesday class. Okay. So I think that's it for today.